Greetings, members one and all of the Salivation Nation. Allow me to introduce to you a breakthrough for the world's strongest silver. Yes, this actually does quite make for a very interesting and fascinating scientific discovery. This paves the way for a new class of super strong materials, and it looks like that perhaps this is something that they will do to strengthen up existing metals, and rather than create new carbon-based materials that we have heard about for sure. Now, graphene is something that you've heard me discuss on this channel and how it could possibly threaten. We haven't heard a whole lot about it lately, and that's probably because they find it very difficult to manufacture, especially considering it's got to be done in a pristine and sterile environment, and to produce mass quantities of it in a stable way is very difficult. But this is something with materials science and nanotechnology that comes to us from this SciTechDaily.com, and I've actually done stories from this publication before. The world's strongest silver being invented. This team has created metals that break decades-old theoretical limit, promising a new class of super strong and conducting materials. And that's just it. It's a matter of preserving its conductivity, because silver is the most conductive metal out there. So a team of scientists has made the strongest silver ever, 42% stronger than the previous world record. But that's not the important point. We've discovered a new mechanism at work at the nanoscale that allows us to make metals that are much stronger than anything ever made before, while not losing any electrical conductivity. That's the important thing, says Frederick Sansoj, a material scientist and mechanical engineering professor at the University of Vermont, who co-led the new discovery. This fundamental breakthrough promises a new category of materials that can overcome a traditional trade-off in industrial and commercial materials between strength and the ability to carry electrical current. The team's results were published on September the 23rd of 2019 in the journal Nature Materials. I'm kind of curious to see if this actually shows up here. This is the report here, the abstract of it. A lot of science here, but apparently you've got to pay to read it all. But nonetheless, it is fascinating to see this. So all metals have defects in their structure. Often these defects lead to undesirable qualities like brittleness or softening. This has led scientists to create various alloys or heavy mixtures of material to make them stronger. That's nothing new, but as they get stronger, they lose electrical conductivity. We asked ourselves, how can we make a material with defects but overcome the softening while retaining the electroconductivity? Said Morris Wang, a lead scientist at Lawrence Livermore National Laboratory and co-author of the new study. By mixing a trace amount of copper into the silver, the team showed it can transform two types of inherent nanoscale defects into a powerful internal structure. That's because impurities are directly attracted to these defects, explains Sanzos. In other words, the team used a copper impurity, a form of doping or microalloy, as the scientists style it, to control the behavior of defects in silver, like a kind of an atomic scale jujitsu. The scientists flipped the defects to their advantage, using them to both strengthen the metal and maintain its electrical conductivity. And you can see from this diagram here that says inside a grain of silver, copper impurities in green have been selectively segregated to a grain boundary on the left into the internal defects, long strands streaming downward. The snapshot from an atomistic computer simulation is part of a recent study showing how impurities can be used to create a new class of super strong but still conductive materials called nanocrystalline nanotwined metals. This form of copper-doped silver is so strong that it's broken a long-standing theoretical limit known as the ideal Hall-Petch strength. And that's pretty fascinating how they do that. That's pretty cool. To make their discovery, the team, including experts from UVM Lawrence Livermore National Lab and the Ames Laboratory, Los Alamos National Laboratory, and UCLA, started with a foundational idea of materials engineering. As the size of a crystal or grain of materials gets smaller, it gets stronger. Scientists call this the Hall-Petch relation. This general design principle has allowed scientists and engineers to build stronger alloys and advanced ceramics for over 70 years. It works very well until it doesn't. Eventually, when grains of metal reach an infinitesimally tiny size, under tens of nanometers wide, the boundaries between the grains become unstable and begin to move. Therefore, another known approach to strengthening metals like silver uses nanoscale coherent twin boundaries, which are a special type of grain boundary. These structures of paired atoms, forming a symmetrical mirror-like crystalline interface, are exceedingly strong to deformation, except that these twin boundaries too become soft when their interspacing falls under a critical size of a few nanometers due to imperfections. So very roughly speaking, nanocrystals are like patches of cloth, and nanotwins are like tiny, strong but tiny threads in the cloth, except they're at the atomic scale. The new research combines both approaches to make what the scientists call a nanocrystalline nanotwinned metal, or twined metal, that has unprecedented mechanical and physical properties, the team writes. That's because the copper atoms, slightly smaller than the atoms of silver, move into defects of both the grain boundaries and the twin boundaries. This allows the team, using computer simulations of atoms at a starting point and then moving into real metals with advanced instruments at the national laboratories, to create a new super strong form of silver. The tiny copper impurities within the silver inhibit the defects from moving, but are such a small amount of metal, less than 1% of the total, that the rich electrical conductivity of silver is retained. That's pretty amazing. So that's essentially like saying you've got still 99% pure silver as opposed to 925 or 958 that we see often in our coins to strengthen them. The copper atoms' impurities go along with each interface and not in between, so they don't disrupt the electrons that are propagating through. Not only does this metal overcome the softening previously observed as grains and twin boundaries get too small, the so-called Hall-Petch breakdown, it even exceeds the long-standing theoretical Hall-Petch limit. The team reports an ideal maximum strength can be found in metals with twin boundaries that are under 7 nanometers apart, just a few atoms, and a heat-treated version of the team's copper-laced silver has a hardness measure above what had been thought to be the theoretical maximum. We've broken the world record and the Hall-Petch limit too, not just once but several times in the course of the study, with very controlled experiments, says Sansos. Sansos is confident the team's approach to making super strong and still conductive silver can be applied to many other metals. This is a new class of materials, and we're just beginning to understand how they work, he says. And he anticipates that the basic science revealed in the study can lead to advances in technologies from more efficient solar cells to lighter airplanes to safer nuclear power plants. When you can make materials stronger, you can use less of it, and it lasts longer, he says. And being electrically conductive is crucial to many applications. So there's good news and bad news with regards to this study. That means if they make this work, then silver will become ever so stronger, and they can use less of it, and it can retain its conductibility, which means there'll be less demand for it. But it's got to be synthesized, it's got to be produced. Now, the other benefit to this is potentially in the world of manufacturing and producing coins and rounds and bars out of this stuff would be very interesting. I'm sure most of us would be fine with 99.2 or 3 or whatever, and the rest of it copper, to have super strong and durable coins and bars and rounds. And imagine what you can do to be able to provide intricate detail that is strong in a particular coin. Now, if you apply this to gold, imagine the possibilities there, because gold is so soft and also very dense. I imagine it'd be more difficult to do with gold, considering the density of the atomic structure of the metal. But very interesting indeed, where science is taking us, and in this case, we're seeing something related to using the already perfect metal out there, silver, and applying a little bit of copper in it to make it better. It's going to be probably much more efficient, probably cheaper too, than working with graphene. Post your thoughts below, and what do you think of this technology and the possibilities that it could hold and the limitations that it could provide, and potential could it wreak havoc on silver demand? Let me know what you think below. Would like to extend a multitude of gratitude to you all for watching, and encourage you to please rate, share this video. Yes, that's right. Share it with all of your friends, your family, your grandmothers, your great-great-grandfather, your nieces, your uncles, your fifth cousins twice removed, a stranger on the street, the homeless, the wealthy, somebody in Sri Lanka. Gotta share it with somebody from Sri Lanka. I need more viewers from Sri Lanka. Please do that. And subscribe.